So, in the last series of videos we will look at some advanced topics. So, today we will look at this very interesting concept known as ensemble modeling, or how do you model when there is a lot of uncertainty in the kind of interactions that underlie your model. What is ensemble modeling? What is an ensemble? So, it is a combination of several things, right, like and in the context of modeling it is the use of multiple models, right. So, there was like one very classic paper on ensemble modeling in by Kupfer et al. In 2007, Nature Biotech. Right, the idea is very nice. So, they have what is known as a core model of TOR signaling, right. TOR is the target of rapamycin pathway. It is a very important pathway in multiple organisms. They studied this in yeast, but the mammalian equivalent of this TOR known as mTOR is very important in cancer and so on. It is a classic signaling pathway that affects so many downstream metabolism, growth and so on. Right. So, the idea is very simple. You have a data set D and you want to build a model, right. But how do you infer this model, right. So, if you were to go about the classic modeling that we have discussed in dynamic modeling and so on, how do you go about this? So, you will essentially fix a model, let us say we now pick M1 and now find a parameter set theta 1 that minimizes some cost function, right. The cost function will sort of include the model, the data of course and the parameter set, right. So, can you minimize this cost function and find a parameter set, right. What is the theta that minimizes this cost function, right. And so, this would be the correct the value of theta that we need to employ in the model. So, now what about model 2, right. You get another theta 2 such that you minimize the cost function, right. So, what is the difference between these two models? It is not just in the parameters, because then I would call it the same model, but it is in fact in the model, yes, or the model structure itself, or what we would call the topology, right. So, this is something that we were discussing in robustness as well, right. So, wherein you have a model M1, a model M2 and so on, and you have sets theta 1, theta 2 and so on, right. So, you can explore, or instead of model you could let us even call it topology, right. How sensitive is the topology to changes, right, or how sensitive is the fit to data based on changes in topology. What happens, let us say I have let us say I have a model of this sort, right. So, now you can ask multiple questions. So, maybe this is represented by K1, K2 and so on, right. So, what happens when I vary K1, or what happens when I remove this interaction? They are potentially two different things, right, because usually when you say vary K1 you will vary it around a particular region which seldom includes 0, basically getting rid of that interaction, but there are different ways to go about this, but essentially there are two things you want to worry about. One is parametric sensitivity analysis and what you could also call the other is topological sensitivity analysis. This is easy, all you have to do is dou ln x, something of this sort, some state variable to some parameter. So, you usually do this because you essentially want to do dou x by dou theta, but then normalize it, which becomes, this is an sensitivity coefficient that is non dimensional. What about this? This is quite tricky. There are various ways you want to start evaluating this, and you can obviously you cannot evaluate a model without considering its parameters. It is always in the context of parameters. So, there are nice Bayesian ways to do it. So, you integrate across all possible models across all possible parameters, right. What is the probability of observing my data such that if I pick a model from this space and a parameter from this space, right. So, there are nice ways to go analyze that, but I am not going to go into those details. I am going to just stop short by saying how Kupfer et al. Went about their modeling exercise and how it is a potentially powerful technique to model complex systems where there is a lot of uncertainty, right. Because if we look at like as we wrap up the course, I will start touching on the harder and more exciting challenging topics, and one of them, a key topic there is how do you model systems under uncertainty, right. You always have uncertainty, you do not know what are the components, you do not know what are the interactions, you absolutely have no idea what the parameters are, right. So, under these conditions how do you model systems and how do you make reliable predictions? So, modeling under uncertainty, how do you go about this, right. So, what Kupfer et al. Did was they had a core model, let us call this M0, right, and then they had a bunch of hypotheses. For them n was 18 actually, right. So, you have different, so these could be represented as different models. In fact, this is M1 which is basically nothing but hypothesis 1, and this is M2, this is Mn, right. So, now how do you pick the best model?
The probability given of data coming from that.
Yeah. So, you can basically maximize the probability of observing the data given a model, right, and a parameter set, right, or you can basically see for which model maximize the probability of observing the data across several parameter sets, right. So, which means that the model is more robust, right. So, you could, so this goes back to something that we have seen multiple times. So, if this is M1 and this is M2, you would say this is a better model. Whole process starts by assuming data are present on the system. You have data of sufficient quality, quantity, reproducibility, whatever, as we
each model and get the parameters,
yeah,
and then I will find the probability. Is that what you are saying?
You and then you, yeah, essentially, right, but there are models which you may not be able to fit, right. There could be overfitting, that is another issue, but there are cases, in this case they claimed they found no overfitting, but again they had very little data, so I am not entirely convinced, but the important aspect is that there are still models that you can't fit, because it is like sort of trying to force a square peg into a round hole, right. That is not going to often happen, but you can try and see if there are some models that give a best fit that is better than the others. So, in fact, they ended up ranking their hypotheses based on how good the model fit was. So, they have a figure where they show the error generated from each model, and they even clustered the hypotheses and so on. And what are these hypotheses, just to give you an idea. So, let us say H1, it says that a particular protein like say TAP42 or something in the model has 2 phosphorylation sites and not one. The core model assumes that there is one phosphorylation site. So, the core model essentially reflects a set of well accepted, more oft repeated assumptions in literature, right. So, most people are convinced that this is the core structure of the model, but over and above this there may be other differences, and these are all put into hypotheses. But the interesting part is there is no reason to have just a single hypothesis. So, you could include H1, H2, H8, H11 and H14, right. So, this could be a new model, right, and so potentially you have 2 to the 18 models if you have 18 hypotheses, right, and that is huge. In that case it turned out that some of the hypotheses were contradictory, so you can't take both into account simultaneously, but even otherwise there were close to 70,000 possible models that one could analyze, right. And what kind of data do you need to answer such questions? So, these are very open, very interesting questions, and they also had a very nice model, a very nice paper on the MSN2 system, which was published in Science Signaling, and that goes in for a more Bayesian approach to estimate the best model and so on. So, I think this is something that one should look at. So, ensemble modeling is quite important when you are trying to model systems under uncertainty, right. And this obviously involves a lot of parameter estimation and so on, and I think we have done enough in dynamic modeling to kind of incorporate these concepts and try to model some complex systems. In today's video, I hope I gave you an overview of ensemble modeling, which is an interesting approach to model biological systems when there is a lot of uncertainty, which is very common, or for example conflicting hypotheses about the function of a particular network. In the next video, we will move on to another interesting topic, which is mainly related to synthetic biology, or how do you design biological systems, or how do you understand the design principles underlying a given biological system.